Okay, let's take a look at part 3 of writing linear functions in a word problem given specific information. So we can write these in slope-intercept form, point, slope, and even standard. Juice bathtub contains 40 gallons of water when it's filled to the top. It takes 8 minutes for the water to drain from the tub. Write the equation. So we have juice bathtub. It has 40 gallons before it starts to drain. We know the situation is draining. So we know at 0 minutes, it is 40 gallons in the tub. Then we also know that it takes 8 minutes for the water to be 0. So in 8 minutes, the water is 0. So we can see here we have our y-intercept and we have our x-intercept. So we can see that our x values is going to represent minutes. Again, typically if you're dealing with time, that is your independent value. And then our y coordinates represent the total height of water in the tub. So total height in the tub. So we have to be specific. It's not how much is drained out of the tub. So we have 2 points, so we can find our rate of change. So we're going to have the difference of the height, so 0 minus 40, compared to the difference of the time, 8 minus 0, gives us negative 40 over 8. So we have a rate of change of negative 5. So each minute, 5 gallons is drained from the tub. We do have our initial value, our y-intercept, so we can use slope-intercept form. In a minute, we'll practice putting this in standard form. So now let's talk about our domain. What is the least amount of minutes the tub's going to drain? Well, that is 0. And we know in 8 minutes, it's totally drained. So from 0 to 8 minutes is our domain. And then the total amount of water in the tub is either 0 all the way up to 40. So from 0 gallons to 40 gallons. This is our range. Now, let's ask, can we just connect the points to make a continuous graph, or is it discrete? So we ask, can we have partial minutes? Yes, we can have 2.5 minutes, 4 3/4 minutes, and so on. Can we have partial gallons? Yes, there's such thing as a partial gallon. We could have 2.3 gallons. So this is going to be continuous, so we can simply connect to represent this function. We're going to connect our data points from our y-intercept to our x-intercept. And now it says how many gallons remain in the tub after 3.5 minutes. So we're going to plug in 3.5 for minutes to see how much water is in the tub. So we have 3.5 times negative 5 and then plus 40. And that gives us 22.5 gallons. Now let's just practice putting our equation in standard form. Standard form is ax plus by equals c. So we have y equals negative 5x plus 40. We need to get negative 5x to the left, so we're going to add 5x. And we have 5x plus 1y equals 40, where a is 5, 1 is our b, and c is 40. Remember, when we're doing standard form, your a value and your b value must be integers. They can't be fractions or decimals. So we're good to go here. Now let's take a look at our last problem for this lesson. Ms. Thomas receives a gift card for Christmas. There is $22.50 left on the card after the 7th use. On the 11th use or swipe, there's $12.50 on the card. We need to write a situation to model the Starbucks gift card. So we have 2 data points. We know that when she swipes it on the 7th time, she has $22.50 on the card. And then on the 11th time, there is $12.50 on the card. So we can see that each time she uses it, the amount of money goes down from the card. So we have 2 points. We do not have the initial value. So we're going to use point slope. So we're going to say $12.50 minus $22.50 over 11 minus 7. So we have a negative 10 as our rise over 4. Since we're talking about money, I'm going to convert this to a decimal. So our constant rate of change is negative $2.50. Now let's use point slope form. Y equals my slope times x minus x1 plus y1. We're going to distribute and then we have 2.5, negative 2.5 times negative 7. That gives us positive 1750 plus the 2250. So we're going to combine the constants. And we can see that the initial amount on the card was $40. So the $40, it was a $40 gift card. And we need to see how many swipes it's going to take before we run out of money, and then decide if it's discrete or continuous. So our X values are the number of uses or the number of swipes, and our Y, again, we have to be specific, is the total money that's on the card, not how much has been used. Our domain, we can use this 0 times. We don't know the maximum amount of swipes before it's $0 on the card. We do know that the least amount of money on the card is going to be 0, and the maximum amount was 40. So let's find our x-intercept by plugging in 0 for y, which is total money on the card, and see how many swipes Ms. Thomas can get. So we're going to subtract the 40. And then we're going to divide each side by negative 2.5. And X, the number of swipes, is 16. So when she swipes on the 16th time, she will have 0 money on the card. So what does the X-intercept represent? The maximum swipes. How many cups of coffee she can get from the gift card. Now, can we connect the points? Can you have a partial swipe? No, Starbucks is not going to run your card 1.5 times. So we just have to plot some data points. And so I'm just going to plug in 4 in for X. And we get 30. So at 4 swipes, she has $30 left. And then we can plug in 8. So you can plug in whatever values you want. And we get 20. And then if we plugged in 12 in for X, we would get $10 left. And so we could plot these points in between as well. We can see they line up. We don't even have to calculate. But this is like swipe 2, swipe 6, swipe 10. So make sure the swipe is on an integer and not a decimal or fraction, a rational value, because we can't have partial swipes. So this represents their Starbucks gift card. Now let's convert this slope-intercept into standard form. Again, standard form is AX plus BY equals C. So I'm going to add 2.5x to both sides. And then 2.5, we need that to be an integer. So if we want to make that a 25, we can multiply by a power of 10. So I'm going to distribute the 10 to every term to make an equivalent equation. And we get 25x, 10 times y plus 10y equals 10 times 40, 400.